In this video, I want to go through a couple more examples calculating equilibrium concentrations. And kind of our steps from the last video is we're going to write the equilibrium constant expression. We're going to set up our ice table. And then once you set that ice table up, you're going to plug your equilibrium concentrations from the ice table into your equilibrium constant expression. So plug the equilibrium concentrations into the expression. And then we had to solve for x. Remembering that x is our change, right? Not necessarily our new concentrations. Once you have x, you might have to plug that back into our ice table to solve for the concentrations. Solving for x, we had essentially three different ways to do it. So our first one is if we had a perfect square. So for something like this, you would have to have initial concentrations that are the same. So if you have two reactants, the concentration of both reactants must be the same. And then you have to have a squared term on both the reactants and product side. So the type of reaction that you have is going to be kind of important. So kind of an example, if I had A plus B going to 2AB, and then if the concentration of A is the same as the concentration of B, you're going to have a squared term on the top and the bottom, right? The top is going to be squared because I have 2 moles of AB, so concentration of AB squared. And then the concentrations of A and B are the same, so on the bottom it's also going to be squared. So initial concentrations would have to be the same. If you had 2AB going to A plus B, right, this in the reverse direction, then it would also work. So just again, you have to have the squared term on the top and the bottom, right? Kind of the definition of a perfect square. And our initial concentrations in this case for A and B would have to be the same. Our second scenario is using that assumption. So we're going to assume X is negligible, basically much smaller than the initial concentration. And we can only use that assumption when our value for Kc is less than 10 to the negative third. So when Kc is small, less than 10 to the negative third, we can assume that X, right, that's the amount that I'm losing, is small, it's negligible compared to the initial concentration. And that makes, again, our math much easier. And then the third scenario is if neither one of those happen to apply, we have to use the quadratic equation. So if you don't have a perfect square, your value for your equilibrium constant isn't less than 10 to the negative third, the quadratic equation is going to be needed to use to solve for x. So I want to go through a couple examples, and I'm going to write down the problem, and then I really want you to just hit pause and work through the problem completely on your own, just like you were on a quiz or an exam. And then after you've worked through it, you can then hit play again to watch me work through it and see if you get the same thing, or if you get stuck, you can, see the solution. So in the problem here, I'm going to have acetic acid, which is CH3CO2, and it's aqueous. It's going to be reacting with water liquid And we're producing hydronium ions, H3O+, which is aqueous, plus acetate ions. Acetate was one of the polyatomic ions that you would have learned in 150 or 151. Our equilibrium constant for this reaction is 1.8 times 10 to the negative fourth. And then we're going to calculate the equilibrium concentrations of acetic acid, hydronium ions, and acetate ions when the initial concentration, maybe we should say if, of acetic acid is 1.75 molar. So please hit pause, work through the problem, and then when you're ready to go through it together, hit play again. Alrighty. So I'm going to write my equilibrium concentration, my equilibrium constant expression first. You could set up the ice table first. Really, that order doesn't matter. I do know that my equilibrium constant, which is equal to 1.8 times 10 to the negative fourth, is equal to the concentration of my products. So hydronium ions multiplied by the concentration of acetate ions, both raised to the first power because there's 1 mole of each. And then that's going to be over the concentration of acetic acid. Water is not part of this expression. Remember, pure liquids and pure solids are not part of our equilibrium constant expression, so that is left out. It doesn't go there. Now that I have that, I'm going to set up my ice table. So I'm just copying my reaction here. Down. Water again, because it's not part of my expression, I'm just going to really ignore it. So my initial concentration, C is my change, and then my equilibrium concentration. So initial concentration, I am given 1.75 molar. Water we don't care about, and then I don't have any of my product initially, right? So 0 for hydronium ions and acetate ions. And then for my change, we're going to lose some unknown amounts. We're going to call it X. We're going to lose from the reactant side. We're going to gain on the product side. Because there's 1 mole of everything, it's just 1X for all of those. And then my equilibrium concentration, 0.175 minus X, right? What I started out with minus what I lost. X, because 0 plus X is X, and then X again. So then I would take those values and plug them into my expression. I do notice, though, that Kc here is small, right? It is less than 10 to the negative third. That's always something I want to look at, because that's going to save me from having to use the quadratic equation. If you didn't notice that and you went through the quadratic equation, we honestly should get the same answer or something very close. So because, let's add this here, because Kc is less than 10 to the negative third, we're going to assume X is negligible compared to initial concentration. So 1.75 minus X is going to be about 1.75, right? We're saying when we subtract X from 1.75, which is my initial concentration, it's so small that it doesn't really matter. So 1.75 minus X is going to be about equal to 1.75. So when I plug these values into my expression, instead of plugging 1.75 minus x into my expression, I'm going to plug in 1.75 for acid or for acetic acid. So doing that, I have 1.8 times 10 to the negative fourth, right? My value for my equilibrium constant. I'm going to have x, right, which is my hydronium ion concentration, times x, which is my acetate ion concentration. So x times x is x squared. And then on the bottom, I'm just going to put the 1.75. Grabbing my calculator to solve for x. I get 0.018 for x. And then remember, x isn't necessarily my answer, right? We're asked to solve for equilibrium concentrations. So my equilibrium concentration for acetic acid is going to be 1.75 minus x. We did assume it was negligible when we plugged it into our expression, right? We did this. Right? We ignored the minus x. That doesn't mean when we're solving for our equilibrium concentration at the end, though, that we can still solve for x or still ignore x, right? If I go back and look at this, I have an about sign, right? It's about equal. We're not saying it is exactly equal to it. So we do want to come back and do that. So when I subtract that, I'm going to get 1.73. Is that right? Yeah. And then don't forget units. So that's my equilibrium concentration. My equilibrium concentration for hydronium ions is x. Again, don't forget units. And then for acetate ions, it is also x. And don't forget units, right? If we go back up and look at our ICE table here, these are my equilibrium concentrations. Once you have those values, I would highly recommend going back, plugging them into your expression. You should get something very, very close to 1.8 times 10 to the negative fourth. One more example for us. And we're going to do the same thing. I'll write down the problem, and then I would really like you to work it on your own. And then you can come back and check the solution. So the equilibrium constant for the following reaction is 129. If the initial concentration of hydrogen is 0.100 molar and the initial concentration of iodide is 0.120 molar, what are the equilibrium concentrations of all species, so all reactants and all products? And then our reaction, we have hydrogen gas plus iodine gas going to 2HI gas. Alrighty, so please hit pause, work on the problem on your own, and then if you get stumped or when you're finished with it, please come back. All right, so I'm going to set up my ICE table. You could set up your equilibrium constant expression first. Again, it doesn't really matter. Since I have the reaction here, I'm just going to write the ICE table right below it, and that's why I'm choosing to do that one first. They're all gases this time, so they are all going to be part of my expression. So initial, change, and then equilibrium concentrations. For hydrogen, we have 0.100 molar. For iodide, 0.120 molar. And then initially I don't have any products. We're going to lose some unknown amount called X. It's 1X for both of those because I have 1 mole of each. And then I'm actually going to gain 2X on the other side, right, because I have 2 moles, right? This 2 is because there's a 2 here. At equilibrium then, 0.100 minus X, 0.120 minus X, and then 2X. I'm going to set up and then plug those into my equilibrium constant expression. My equilibrium constant is 129, so it's not less than 10 to the negative third, so we can't use that assumption this time that it's small, because it's not. So I do need to square the concentration of hydrogen iodide because I have 2 moles of it. And then both of these are raised to the first power. And then I'm just going to go ahead and plug everything in. So for HI, I have 2X, and then be really careful, we're squaring the entire thing. It's actually going to come out to be 4X squared. It's a really common mistake for students to just do 2X squared. So it's not 2X squared, it's 2X squared. So make sure that you get those parentheses around there. And then that's over 0.100 minus X multiplied by 0.120 minus X. So we've already stated that we can't use the KC is small assumption. And for this one, I don't have a perfect square neither. This type of reaction does fit into the type that we had above, where a perfect square was an opportunity, right? I have a square term on the top, and if this number and this number were the same, I would also have a square term on the bottom. But we had said that the initial concentrations have to be the same for that to happen, and they're not. Because the initial concentrations are not the same, I don't have a perfect square, so we are going to use our quadratic equation to solve this problem. You don't need to memorize it if you don't already know it. I will provide it on exams. I'm just moving it up a little bit so I have enough room here. I know some folks have calculators where you wouldn't actually need to use this form, right? Your calculators will do it for you if you have a polysolver function. I know my calculator does, but the calculators that you're supposed to be using for this class would not have that function. So when you're doing problems where I'm looking at your work, I do want to see everyone doing the math and plugging it into the quadratic equation. So the algebra that it takes to get it to the quadratic equation, plug it in. I want to see all of that. So we need to get it in the form of ax squared plus bx plus c equal to 0. So a little bit of algebra to get it into that form. So I'm going to do that. We'll do the FOIL method on the bottom there. And then multiply both sides by that expression on the denominator, distribute. $125, sorry. All right, so A is 125, B is a negative 28.4, and then C is 1.55. So we are going to take those values, plug them into my equation. So x is equal to negative b. Since b is already negative, it becomes positive, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And then we will do the math there. We are going to get two values, right? I'm doing plus or minus, so 28.4 plus the square root and everything underneath it, and then minus again. So we do get two values. So back to my calculator. And I have 0.136 or 0.0911. So those are our two options when I solve that. I did solve it earlier, so that's why it was so quick. It would take me a little bit longer to do that math. So remember we said one of these two values we need to throw out. When we did the example in the last video, one of my values for x was negative. And remember what x is representing. X is the amount of reactant that's reacting to reach equilibrium. And a negative amount cannot react. So if you had a negative value, it makes no sense. So that's the one you would get rid of. Here, they're both positive. But if I go back up and look at my initial concentrations, one of them was 0.100. The other was 0.120, right? That's how much we had to begin with. I can't lose 0.136 if I only started out with 0.100, right? We can't lose more than we started out with. So this value is larger than my initial concentration, so that doesn't make sense. So this is the one that we want to choose. So we're not quite done, right? We still need to solve for our equilibrium concentrations, right? Right now we just have x. So I need to plug those back in, right? My equilibrium concentration for hydrogen is 0.100 minus x, right? For iodide, 0.120 minus x, and then for hydrogen iodide, 2x. So doing that work, and I'm just going to set them all up and then do the math after. And then for the first two, for the concentration of hydrogen and iodine, be careful with sig figs. We are using our addition and subtraction rule, which is the number of digits after the decimal point, not the actual number of significant digits. So for this one, I get 0.009, which is only one sig fig, but again, we're using a different rule. So I have 3 after the decimal point, 4 after the decimal point, 3 digits after the decimal point. And then for the last one, we're multiplying, so different rule for sig figs. And then also don't forget units, right? We are solving for molar concentrations, so don't forget to put those values on there. So these are my equilibrium concentrations. For something like this, I would definitely go back up. I mean, I always think you should, but if you're not going to do it every time, do it this time for sure. There's a lot of math here, and there's a lot of places to goof up. Like you can just type something into your calculator incorrectly, write something down wrong, even if you're doing the steps correctly, and it can throw everything off. So I would plug them back in. Again, there was quite a bit of rounding, so it's not going to come out perfect, but it's going to come out pretty reasonable. If you plug them back in, you get like 172 or like 0.3, like something went astray. Let's actually do this one together. So 0.182 squared, right? I'm just taking these values here right? These ones. And I'm going back up to this and I'm plugging them in, and I should get 129 as my answer. Again, it's not going to be exact this time, and it'll probably be a little bit further off than usual, but it's going to be in the ballpark. If we did it right, I should say. So I got 126.9, so 120, writing with my highlighter, 127 when I plugged them back in. So I'm cool with that.